Good morning, Mr. Eicher here to teach you a Math 3 lesson about recursive functions, Chapter 9, 9.0. So make sure you look for those notes. You can print those and follow along. It'll be a good idea. So, first off in this chapter, we're talking about what are called sequences and series. Sequences are patterns with some kind of particular order, some kind of pattern to the number sequence. So those are sequence. This lesson and the next couple lessons we'll talk about sequences. So if you'd like to pause the video and see if you can figure out what the next number would be, or the next two numbers in the patterns in A, B, and C that we have before us. One approach you can do to figure out the pattern, maybe you could say, well, 3 to 3, that's changing 6, you're adding 6. And then 3 to 9, you're adding 6. 9 to 15, you're adding 6. This is a good pattern so far. And then 15 to 21, you're adding 6. So it looks like our pattern is you add 6 each time. Add 6 to get the next term. That says next. So what a recursive formula or recursive function is, basically you say where your starting point is. So our recursive formula for this sequence, we started at -3. So it's kind of like function notation a little bit. You would have A of 1. That's our first term. Oh, that's really small. I need to change that. The first term, A of 1, or A sub 1, sometimes we'll write it. The first term is -3. And then to get the next term, we add 6 to that. So the next term would be the second term. And we're adding 6 to that, -3 plus 6. So that term would be -3. That's what we had, -3. And then the term after that, the third term, A of 3, the third term, would be that -3 plus a 6 plus another 6. Or we can actually write it as whatever that previous term was. The previous term we had was +3, and we're adding 6 to that, which is 9. And our fourth term would be 9 plus 6, and that is 15. So can we write this in general? What would our recursive formula or recursive function be? Well, when defining a recursive formula, you're going to have this first term where you start, and then how you get the next term. So the notation, really this whole lesson, my goal, is to get you used to the idea of what a recursive function is and understand what the notation means. So I'm going to erase these, you don't have to erase yours, but I'm going to erase 2, 3, 4 here. And let's see if we could come up with a general recursive function. So if this is our first term, then our next term, which we'll just call n, would be our first term plus 6. So if we put a 2, if we wanted A sub 2, we'd plug -3 in and get -3 plus 6 to get +3. Now this doesn't always work though, because for instance if you would put like a 3 here, that's not just the first term plus 6. You'd have to do like the second term plus 6 to get the third term. Or if we put 4 here, that wouldn't work, because for the fourth term should be 15, but this just says take the first term plus 6. So really we have to change this. This should be changing, like if this is a 4, then we should be adding the third term here. So the way that we address that is we're going to have a sub n, whatever term, n term we're on, we want to take a of the term before it, n minus 1, and then that's what we add that's what we add 6 to. So this notation can be a little tricky, like understanding what this is representing and what this is representing. So let's just try this. If we had a of 5, to figure out the fifth term, we would need to know the 5 minus 1, the fourth term, and we'd add 6 to that. So that looks like it's working. Like whatever number you put in here, 5, you're going to subtract 1 from that, and that's going to represent the previous term, 4. So our recursive formula would be our starting point, this guy right there, and this, minus the green circles, and that would be our recursive formula. Now there's also what's called an explicit formula, which you're probably a little more used to. And let's look at that next. For an explicit formula, you can think of it basically as how would you write in a function that is the first term is -3, the second term is 3, the third term is 9, the fourth term is 15, and think of it in terms maybe of an xy table. So what type of function would this be? Would it be linear, quadratic, exponential, logarithmic? Hopefully not logarithmic. Well, we said that these differences are 6. So that's the rate of change. The rate of change is 6. So the rate of change is basically the slope. So in this particular sequence, we could write an explicit formula that looks kind of like y equals mx plus b, where m is the slope of 6, and the y-intercept, well, the y-intercept, we'd have to do a little bit of thinking. The y-intercept is going to be whenever, let me get a little more space up here, the y-intercept is whenever the x is 0, what the y equals. So what does the y equal? Well, if we keep going backwards by 6, we'd have what, -9? So subtract 6, -3 minus 6 to get -9. So it looks like our explicit formula would be y equals 6x minus 9. And we can see if that works. If we plug 0 into this, that all would be 0, and that would be -9, so that works. If we plug 1 into this x, that would be 6 times 1 minus 9 is -3, that works. If we plug 2 into this, that would be 12 minus 9 is 3, so that works. So our explicit formula, our explicit function, turns out to be a linear function, 6x minus 9. So those are recursive and explicit functions. Let's look at the next example in B. I have to get rid of some of these. There we go. So in B, let's see how these numbers change. We have 1 to 3, that's a difference of 2. 3 to 7, that's a difference of 4. Notice this isn't a common difference, so it doesn't look like we're going to have a linear function here. But then 7 to 15, that's a difference of 8. 15 to 31 is 16. And 31 to 63 is a difference of 32. So these numbers look familiar, don't they? 2, 4, 8, 16, 32. Those are numbers that if you have like 2 to the first, that would be 2. 2 squared, that would be 4. 2 to the third, that would be 8. 2 to the fourth, that's 16. 2 to the fifth is 32. So these are powers of 2. So let's figure out a way to write a recursive function for this. So with recursive functions, we have to figure out where we start. So where we start, the first term is 1, so a of 1 is 1. That's our starting point. Now what would we have to do to get the next term? Well, based on this pattern, we need to add multiples of 2. So the first time we're going to add just 2. So maybe we could try this. To get our second term, we would take our first term plus 2 to the first, right? And that would be 3. To get our next term, our third term, we would take our previous term, which was all that, 1 plus 2 to the first, and then we would add 1 plus 2 to the first. So we'd take that, and we need to add 2 to the second. All right, that would be 3 plus 4 is 7. 7, check. And to get our fourth term, we would need to take, this is a lot to write, we need to take 1 plus 2 to the first plus 2 squared, and then we need to add 8 to that, which is adding 2 cubed. So it looks like there's a pattern here. We're always adding a multiple of 2, and the amount that we add increases, this exponent increases. So, but the problem is we have to generalize this. We'd like some function that would work that if I wrote a to the n equals, and one function to figure out the term before it plus the new factor. So we would like the term before it, so all this stuff right here, we'll start at a of 2. This stuff right here was the term before it. This stuff right here was the term before it. This stuff right here is the term before it. So I need to add the term before, so that would be a of, I don't like this line, a of n minus 1. And I need to add some multiple of 2. So what exponent should I use on that? Well, let's look at the pattern here. This exponent, how does that compare to the term that we're on? Or this exponent, how does that compare to the term we're on? And this exponent, how does that compare to the term we're on? Well, it looks like comparing these, that's it's just 1 less. 3 to 2, 2 is 1 less. 4 to 3, that's 1 less. So it looks like it'll work to have our exponent be whatever term we're on minus 1. So let's see if this is going to work. Let's put 2 in here. And we should get 3 as a result. So a of 2. A of 2 would be the first term right? 2 minus 1 is 1. So the first term plus 2 raised to the 1 minus 1. 2 raised to the 1 minus, n is 2 here. So 2 raised to the 2 minus 1 is plus 2. So this would be, the first term is 1 plus 2 to the first, which is 3. And that's what we should get. Let's try this again. Try the third term. The third term would be, looking at this right here, the third term would be the term before it, a of 2, plus 2 raised to the 3 minus 1. The term we're on is 3, n is 3, minus 1 is 2. So the term before it is 3. So the third term, the term before it is 3, plus 2 squared, and that would be 7. So our third term is 7. So it looks like this pattern works. Now there are other patterns that you could write rather than this, but this is a really good example, this right here, of an explicit function, probably like one of the most complicated explicit functions that we would see. We have one more example here on C, and that might look a little complicated. But let's see if we could figure out an explicit function. See that I've written really bigly, so let me erase some of these things. So an explicit function. How would we figure out an explicit function? Well, maybe you notice this. Like this number is 1 less than 4. This number is 1 less than 8. This number is 1 less than 16. This number is 1 less than 32. And this number is 1 less than 64. So maybe for our explicit function, we would be able to write something in terms of these multiples of 2. So let's just try something. So let's see. How about we do 2, let's try this for our explicit function, 2 to the n, okay? So we'll say our explicit function is a of our nth term equals 2 to the n. So let's see if this works. If we plug 1 in, that would be 2 to the 1, so that would be 2. Is our first term 2? No, but it's really close. It's only 1 away. So this function as we've written it isn't going to work. But maybe if we try that function as I've written it and then subtract 1 from that, minus 1, maybe it'll work then. So now if we do a of 1 equals 2 to the 1 minus 1, so that would be 2 minus 1 is 1. So that's good. Let me try 2 more terms. Let's say we have the second term. A of 2 is the second term. And that would be 2 raised to the 2 minus 1. That would be 4 minus 1 is 3. And that's good. Should equal 3. Okay, one more term, and then we can be confident that it's going to work for all terms. A of 3. That would be 2 cubed minus 1. That's 8 minus 1 is 7. And 7 is what it should equal. So it looks like our explicit formula is this a of n equals 2 to the n minus 1. And maybe there are other possible explicit formulas too. But an explicit formula is basically you can plug any n in. So if I wanted like a of 10, I could just pretty quickly figure out that it's 2 to the 10 minus 1. So that's an explicit formula. A recursive formula, you'd have to know like the 9th term to find the 10th term. You'd have to know the 8th term to find the 9th term. So one reason why we rely on explicit functions is sometimes they're easier to calculate. Just plug a number in and you can find whatever term that you're looking for. Let's look at one more sequence. Now, some of you may recognize this sequence. It's maybe one of the most famous mathematical sequences there is. But you could pause the video and see if you could figure out what would the next number be in the sequence. Okay, so the next number you would get, let's see, is 55. We're able to get 55. The number after that would be 89, and the sequence continues. This sequence, anybody know? Anybody? Anybody out there? Anybody? This sequence is called the Fibonacci sequence. There are many applications of the Fibonacci sequence, particularly in nature, which is really cool. But this sequence is named after an Italian mathematician, Fibonacci. I don't think he was the first to discover it, but he got the credit for discovering it. But what is the pattern? Well, the pattern, if you didn't figure that out, the pattern is you take the two terms, so like this 3 right here, you take the two terms before it, this 1 and this 2, and you add them to get 3. This 21, you take the two terms before it, you add them, and you get 21. So basically, let's see, to get any term equals the term before it plus the two terms, the second term before it. So you have to go 2 before it and then 1 before it and then add them. Now, you might be thinking earlier that you like explicit functions a lot better, you're more used to them, who cares about these recursive functions? Well, for this Fibonacci sequence, I don't think you can actually write it as an explicit function. Since it's based on two terms before it, you would need to write it as a recursive function. So we're not going to try to write an explicit function here. We're just going to write a recursive function, a recursive formula. So let's try to write this out and see if it works. So let's say we want any term. So that's just a of n, whatever term we're looking for. I'm using a subscript here. You could also use the notation with parentheses, either one. Maybe I'll start with the parentheses since that's what we've been doing in this lesson so far. So a of n is some term. So we would have the term before it would be n minus 1. So if you're on the 10th term, the term before it is the 9th, so you subtract 1 from that. And then you add that to the second term, the two terms before it, which would be n minus 2. So for instance, what this is saying is, if you want the 10th term, for instance, you would have to take the 9th term plus the, you'd have to do the 9th term, a sub 9, plus the 8th term, which is a of 8. And that's exactly, this right here is exactly what the Fibonacci sequence is doing. So this would be our recursive formula. However, we can't really go into negatives. At least the Fibonacci sequence isn't defined for negatives. So the Fibonacci sequence is, you have to be told the starting point. So you would be told a of 1, the first in the sequence is 1, and you'd be told that the second in the sequence is also 1. And then with that information, I'll include that as part of my recursive formula. With that information, we've defined the Fibonacci sequence. I'd like to go right above here and finish this other notation because it's actually kind of more common than using parentheses. This a sub n part right above the blue box would be a of n minus 1 plus a of n minus 2. So you can use subscripts to write this function, the Fibonacci sequence. So let me just show you a couple examples. So if we want the third term, we would take the second term plus the first term, and the second term is defined as 1, and the first term is defined as 1. So we would get 2 for our third term. If we wanted our fourth term would be the third term plus the second term, and so that would be our third term we just found is 2. Our second term is defined right here, which is 1. So our fourth term in the Fibonacci sequence is 3. And then one more just for good measure, so you can get used to the notation. It's a big point of today's lesson is getting used to this new notation. If we wanted our fifth term, I think we're on, our fifth term would be our fourth term plus our third term. Our fourth term that we just found is 3. Our third term is 2. So that means our fifth term is 5. It just so happens that the fifth term is 5. So that is the Fibonacci sequence. So a couple notes about notation to close off this video. Recursive function notation. So a sub 1, that would be your first term. That's typically our starting point. And then a sub n is any nth term that you'd like to look for, any nth term. So if n is 8, that would be the 8th term. A sub n minus 1, that would be the term before a sub n. And maybe if we had a sub n minus 2, like the one we just had, that would be 2 terms before. 2 terms before a sub n. Maybe if you have a sub n plus 1, you want to take a guess what you think that might mean. A sub n plus 1. That would be the next term. After a sub n. So, in this video, we looked at recursive functions and did a little bit of work with explicit functions. But I hope that this lesson will help you get used to this notation that we're going to be using throughout this chapter about sequences and series. Thanks for watching.